Are we alone in the universe? When you look up at the stars, does it happen that someone from another civilization is looking at you? This problem has been accompanied by the development of astronomy. When we realize that the other planets in our solar system are worlds as vast as Earth. When we realize that orangutans are actually other suns. When we realize that many of the objects called nebulae are actually galaxies like the Milky Way. We are constantly broadening our horizons. But in the end, there was a hard limit. The boundaries of the observable universe. Because the speed of light is limited. 300,000 kilometers per second, and the universe does not exist forever. It only existed for 13.8 billion years. Multiply these two numbers together. We have a limit. That is, since the birth of the universe. Light can only travel so far. So we can't see beyond that limit. Currently estimated. The diameter of the observable universe is about 903 billion light years. That's right. That's more than twice what it was in 13.8 billion years. But that's because since the birth of the universe, has been continuing to expand. Beyond the observable universe. We can't determine what happened there. The universe is finite or infinite. Still flat, these problems can only be left to the future. As far as today is concerned, we have just defined the scope of exploration. 903 billion light years. Within this range, we will explore whether life exists. Does intelligent life exist? And what their proportions are. This requires us to make a lot of assumptions. Because of the stars, the populations of planets and galaxies remain unknown. Luckily, this is a rapidly developing area of research. Maybe in the next 10 to 20 years, we can see the exact evidence. Let's first define what we're looking. Earth is a rocky planet located in the habitable zone of a yellow dwarf. And yellow dwarfs belong to stars like the Sun. Based on these parameters only, we'll be able to make some interesting calculations. In the universe, the most common stars seem to be red dwarfs. These very small stars are extremely long-lived. They make up about 73% of the total number of stars in the Milky Way, may also account for 73% of the total number of stars in the entire universe. According to our first definition, we'll talk about this later. Next is Chin-Nixin. Such stars are slightly larger than red dwarfs. Life is also slightly shorter. They also don't fit our definition. But some researchers believe they may well exist for life. So we will also pay attention to them. Orange dwarfs account for about 13% of the total number of stars in the Milky Way. Yellow dwarf. That is, the number of our first focus targets ranked third. It accounts for about 6% of the total number of stars in the Milky Way. For every Sun-like star, there is one orange dwarf star and 12 red dwarfs. We can ignore stars larger than these three classes, because they have a very short lifespan. Life is hard to develop around them. According to the determined proportion, we can start making preliminary estimates. First of all, from the galactic point of view, the exact number of stars in the entire galaxy cannot be determined. Probably in the tens to hundreds of billions. So, we use this as a basis for estimation. If the proportions given earlier apply, this means that there may be 6 billion to 204 billion Sun-like stars in the Milky Way. This is already a considerable amount, if they're not already occupied. This means that each person gets 1 to 3 yellow dwarfs. We can't calculate how many yellow dwarfs there are in the real universe, so today we're only talking about the Milky Way. The observable universe extends 903 billion light years. And our galaxy is only 100,000 light years across. So, we also need to do a lot of multiplication. It is estimated there are only about 0.2 billion galaxies in the observable universe. Some are smaller than the Milky Way. Some are larger than the Milky Way. So we need to multiply the number of 6 billion to 204 billion yellow dwarfs in the Milky Way by the number of 0.2 billion galaxies in the observable universe, to find out how many Sun-like stars there are in the observable universe. If we are alone in the universe, all these resources belong to mankind. We don't have to worry about energy, don't worry about crowding. Before that, we need to use a set of methods to screen. Remove those that are not appropriate. Actually, we are not interested in all these stars. Some are very young. Their potential planet hasn't had enough time to develop. Some are older, coming off the main order. Their planetary systems are not in good shape either. It seems that the formation of most stars and planets is very different from what we see in the solar system. We've discovered a lot of hot Jupiters. They orbit the yellow dwarf. These giant planets are very close to their stars. And we're interested in the rocky planets that are within the migration zone. Those giant gaseous planets are excluded from the system in a study published in 2002 based on data from the Taihan Observatory. provides us with a figure that is suitable for use here. 10 to 20% of Sun-like stars may have a planetary system identical to ours. We average that number. Suppose 15% for the galaxy. This means that there could be 0.9 billion to 3.6 billion planetary systems similar to ours. Each such system probably has at least one. There are up to 30 rocky planets in its habitable zone. According to our previous ratio, we will have 1 to a billion planets that fit our first definition in the galaxy. Of course, this number needs to be multiplied by 0.2 billion to cover the entire observable universe. It is unlikely that all of these planets have vast oceans, green grassland, and an environment suitable for living. Being in the habitable zone does not mean being a habitable planet. Just look at the Moon. He's completely in the habitable zone of the Sun, just like the Earth, but that doesn't make him a habitable planet. Despite this, we've got a problem here. We don't know exactly what makes the planet habitable. Is the exact distance of its size from the Sun, his magnetic field, its chemical composition is still its massive satellite. Do these elements have to be strictly reproduced to form an environment like ours on Earth? We also encounter here the limitations of observational astronomy. It's impossible to know for sure whether a rocky exoplanet has moons or magnetic fields, so we can't assess the proportion of truly habitable planets. However, there are strict screening criteria. The number of planets that can meet all the conditions will be greatly reduced. In the solar system, large moons around rocky planets appear to be rare. Only the Earth has one. The same is true for strong magnetic fields. Venus is almost as big as Earth. And it didn't. So is Mars, although Mercury is in the middle. So to recreate the exact conditions on Earth, we may need to divide our sample by 10 or even 1,000. The good news is, even if we are very strict in dividing, but the number of planets to choose from is still huge. In the Milky Way alone, there are still millions of such planets. So much so that we're like Enrique Fermi said, life should flourish everywhere and should be detectable. There are dozens of ways to look at the Fermi paradox, have a chance to talk to everyone. However, that is why we retain, is because some of these solutions may come with tighter filtering. Time filters, for example. The solar system has existed for 4.5 billion years. Intelligent life has only been in existence for 4,000 to 5,000 years. If we only care about the time that intelligent life exists, that time period could reduce the number of planets in the Milky Way that might have had life from the millions to just a few. Maybe not even one. In other words, Earth civilization is not worth mentioning briefly on the time scale of the galaxy. The range of observable universes and galaxies is vast. A civilization can only last a few hundred to a few thousand years, and be able to communicate electronically. Then it is most likely to be found by other civilizations within a few hundred to a few thousand light years. Although this involves a lot of stars, but compared to the total number of 0.1 billion to 0.4 billion stars in the Milky Way, this number is still much smaller. The purpose of our search for Earth-like planets is important. If it is to communicate with an alien civilization that may have radio communication, then there is no point in looking for planets more than 100 to 1,000 light years away. Likewise, if it's for interstellar travel, we should also pay more attention to planets within 5 to 10 light years. Because even reaching the nearest Proxima Centauri system, it also takes a lot of energy and effort. There may be billions or even trillions of Earth-like planets in our observable universe. If every galaxy has at least one civilization, at least 0.2 billion civilizations exist. But these civilizations and planets are too far away for us, not accessible through communication or travel. We should focus on the planet closer to us, like a planet within 50 light years. Within this range, we estimate that there are about 500 yellow dwarfs like the Sun. About 100 of them may have planetary systems similar to our own solar system, while it is unlikely that intelligent civilizations will be found in these systems. But the chances of finding some planets that support simple life or future colonization are much higher. We've only been looking at stars like the Sun. But actually there are more orange dwarfs and red dwarfs within 50 light years. We found about 1,500 orange dwarfs and 5,000 red dwarfs. These stars are dim because they are dim, so it's hard to detect from 10 to 20 light years away. The ICS system is a system of red and brown dwarfs. 22 light years from us. It was not discovered until 2013. Many rocky planets have been found around these stars. One of the most striking is the TPS-1 system. It has 7 planets similar in size to Earth. 3 of these are in the habitable zone. These stars are very stable. It is expected to live longer than the Sun. So within 100 light years, we have a lot of interesting planets to study. However, it is difficult to determine whether these planets are really exoplanets. Red dwarfs are some very faint stars. Their habitable zone is very close to the star. The planets that lead to revolve around them are often one side forever facing the star, like the day forever. On the other side is the eternal night. In addition, red dwarfs are prone to eruptions. A planet in its habitable zone would be subject to 400 times more IK rays than Earth. This makes us question whether there really are habitable planets around red dwarfs. If such a planet is found near our solar system, then our previous estimate of the number of exoplanets may have to increase by at least 10 times. If not, then there may be fewer habitable planets around red dwarfs. Orange dwarfs are located between red and yellow dwarfs. They have a shorter lifespan than red dwarfs, but longer than a yellow dwarf. Orange dwarfs send fewer X-rays into the habitable zone than red dwarfs, but more than yellow dwarfs. It is about 25 times the size of the Earth. Still, Chen dwarf stars emit less ultraviolet light than the Sun. This makes them an ideal place to look for life. In June of this year, scientists have announced the discovery of 3 super-Earths around a Chen dwarf star 55 light-years away. One of them is in the habitable zone. The revolution period is 151 days, which means it may not be spinning in sync. Have a more ideal day and night replacement. If there are indeed 1,500 dust stars in the vicinity of the solar system, then we have a good chance of finding a truly migrating exoplanet. If such a planet is less than 10 light-years away, that may be worth the huge effort invested in interstellar travel. Thanks for watching. Welcome to the Civil Science Brigade. To leave a message and put malicious words.